Hello, I am Abdallah Alansaari, a PhD graduate from Khalifa University under the supervision of Dr. Igor Boyko. In this video, we will talk about our project on satellite attitude control. And here we have a magnetically levitated satellite that provides frictionless rotation on a single axis of freedom. This mimics the frictionless rotation a satellite experiences in space, however constrained to a single axis of rotation. The main objective of this work is to achieve attitude stabilization and maneuvering or reorienting of the satellite in space with optimal performance under modeling uncertainty. So how can we achieve optimal performance for any satellite that we have? Our approach is based on two steps. The first step is a test, which is based on two relay feedback control that induces certain oscillations in our system. By designing our test parameter, we can vary at which point we want to induce oscillations or at which phase angle of our plant dynamics we want to induce these oscillations. And then the second step is that taking these oscillations amplitude and frequency and to map them to optimal gains for our PID controllers. This mapping is what we call optimal tuning rules. These two steps are done in coordination, in a sense that our test parameters are coordinated with our tuning rules in order for us to achieve optimal performance with certain specifications on phase margin. In order to find the optimal test parameter that is coordinated with our tuning rules, we employed offline simulations for a class of satellites with varying time delays and actuator dynamics. Upon this offline simulations, we were able to find the optimal test parameter and the optimal tuning rule that relates this test parameter to the optimal transient performance of our satellite maneuver or change in attitude. Using this experimental setup, we were able to validate our theory. The first step is to calibrate the gyro readings. Since that we are using the gyroscope measurements to get the angle of rotation, we need to remove any biases in the measurement by having the satellite on a stationary service. The next step is to preload the reaction wheels. So we set the reaction wheel speed at a constant value. After reaching a steady state speed, now we place the satellite on this magnetic levitation setup. It can rotate freely. Now we want to stabilize the satellite using a PD controller, and we are using some initial gains which are not optimal. So now we have it stabilized. If we move it, it goes back to its location. And now we show our method of non-parametric auto-tuning of satellites under uncertainty. So now I'm running the two relay control, which as you can see, induces certain oscillations in the system. We can see the oscillations here. We measure the amplitude and frequency, and then we obtain optimal PID gains. Now we update the system with those new gains that we have, and we perform a step test. 10 degrees, back to 0, minus 10 degrees, and again to 0. And it is optimized in a way to minimize this transient performance using ITAE, integral time absolute error. So that's the criteria that we are trying to minimize here. In order for us to validate that the PID gains that we have currently are the optimal ones, what we do is that we start from these optimal gains and then we increase, let's say, the proportional gain by 20% while leaving the other gains the same. And then we do the other way, so we decrease it by 20% and so on. So we move away from this optimal point, and every time we measure this ITAE criteria, and we can see that in all four directions that we are going, we always achieve worse ITAE value, which means that we are actually within a close proximity of the true optimal gains. Thank you for watching.